Welcome to today's class on functional analysis. Today we discuss some consequences of Hanbanach extension theorem. So theorem, let X be a normed space over K. Let 0 not equal to A belongs to X. Then there is some f in X12 such that f of A equal to norm A and norm F equal to 1. Consequently, norm A equal to supremum modulus of f of A such that f belongs to X12, norm of f less than or equal to 1. B. Let Y be a subspace of X and A belongs to X but A does not belong to Y closure. Then there is some f in X12 such that f restricted to Y equal to 0, f of A equal to distance between A and Y closure and norm f equal to 1. Consequently, X belongs to Y closure if and only if X belongs to X and f of X equal to 0 whenever f belongs to X12 and f restricted to Y is 0. C. Let A1, A2, etc. Am be linearly independent set in X. Then there are f1, f2, etc. fm in X12 such that fj of ai equal to delta ij for 1 less than or equal to ij less than or equal to m. Proof of A. Consider y equal to set of all ka such that k belongs to k and g of k equal to k times norm A for k belongs to k. Then y is a subspace of X since for x y in y, k l in k, we have x is equal to some k1a, y is equal to some k2a for k1, k2 belongs to k for lx plus my. This is equal to l k1a plus m k2a. This is equal to l k1 plus m k2 into a. So this clearly belongs to y. Therefore, y is a subspace. And we have norm g is equal to supremum modulus of g of y such that y belongs to y and norm y is less than or equal to 1. So this is supremum modulus of g of some ka such that k belongs to k, a belongs to x and norm ka less than or equal to 1. So this is supremum. So we have g of k is k times norm A, k modulus of k into norm A such that k belongs to k, a belongs to x, norm of k less than or equal to 1. So this is supremum modulus of k into norm A such that k belongs to k and modulus of k into norm A is less than or equal to 1. So this is 1. Therefore norm G equal to 1. Hence by Hanbanach extension theorem, there exists some f in X12 such that f restricted to y equal to g and norm f equal to norm g, that is equal to 1. We have a equal to 1 into a and 1 belongs to k. Therefore f of a, this is equal to f of 1 into a, this is equal to g of 1 into a because 1 into a belongs to y. So this is 1 into norm A. So that is norm A. That is f of a equal to norm A. We have modulus of f of a less than or equal to norm f into norm A. This implies modulus of f of a is less than or equal to norm A since norm f is 1. Therefore, modulus of a is greater than or equal to supremum modulus of f of a such that norm f is less than or equal to 1. Take this as equation 1. Now, on the other hand, we have f of a equal to norm a. Therefore, modulus of f of a equal to norm a, because modulus of norm a, that is norm a equal to modulus of f of a, and you know this is less than or equal to supremum of modulus of f of a such that f belongs to x12 and norm f is less than or equal to 1. That is, norm a is less than or equal to supremum modulus f of a such that f belongs to x12 and norm f is less than or equal to 1. This is equation 2. So from 1 and 2, norm a equal to supremum modulus f of a such that f belongs to x12 and norm f is less than or equal to 1. So this proves part A. Now we prove part B. So we have y is a subspace of x. Therefore, y closure is a closed subspace of x by 5.2a. Consider the quotient space x over y closure. Now since a does not belongs to y closure, the coset a plus y closure is not 0 in x over y closure. Therefore, by A, part A of this theorem, there exists f tilde in x over y closure dual such that f tilde of a plus y closure. So this is an element here. This is equal to quotient norm of a plus y closure and norm f tilde equal to 1. So this is just an application of part A. Define f from x to k by f of x equal to f tilde of x plus y closure for x in x, then f equal to 0 on y, and f of a equal to quotient norm of a plus y closure. So because f of a is f tilde of a plus y closure, so that is equal to quotient norm of a plus y closure. This is equal to distance between a and y closure. This is because since we have quotient norm of x plus y is infimum norm of x plus y such that y belongs to y. Therefore, quotient norm of a plus y closure is infimum of norm of a plus y such that y belongs to y closure. So this is nothing but infimum norm of a minus y such that y belongs to y closure, or minus y belongs to y closure. So this is nothing but distance between a and y closure. So now we prove norm f equal to norm f tilde, and you know norm f tilde is 1. So norm f equal to 1. For all x in x, we have modulus of f of x. This is equal to modulus of f tilde of x plus y closure by definition of f. So this is less than or equal to norm f tilde into quotient norm of x plus y closure. So this is equal to norm f tilde into quotient norm of x plus y closure is infimum norm x plus y such that y belongs to y closure. So this is less than or equal to norm f tilde into norm x since 0 belongs to y closure. Therefore, norm f equal to supremum modulus of f of x such that norm x less than or equal to 1. So this is equal to supremum. So this is less than or equal to supremum norm of f tilde into norm x such that norm x less than or equal to 1 from this. So that is nothing but norm f tilde into supremum of all norm x such that norm x is less than or equal to 1. So this is norm f tilde into 1. So this is norm f tilde. That is, we have norm f is less than or equal to norm f tilde. This is the first equation. Now for y belongs to y closure, we have modulus of f tilde of x plus y closure. This is equal to modulus of f tilde of x plus y closure since y belongs to y, and this is equal to modulus of f of x plus y by definition of f, and this is less than or equal to norm f into norm x plus y. So since this is true for x and y, for y in y closure, that is modulus of f tilde of x plus y closure is less than or equal to norm f into norm of x plus y. It will be less than or equal to norm f into infimum of all norm x plus y such that y belongs to y closure. So this is equal to norm f into, this is quotient norm of x plus y closure. Therefore, norm f tilde, this is equal to supremum modulus f tilde of x plus y closure such that quotient norm of x plus y closure is less than or equal to 1. And from this, we have this is less than or equal to norm f into supremum quotient norm of x plus y closure such that quotient norm of x plus y closure is less than or equal to 1. So this is equal to norm f into 1, that is norm f tilde less than or equal to norm f. This is equation 2. Therefore, from 1 and 2, norm of f equal to norm of f tilde, and we have norm of f tilde is 1. Therefore, norm of f equal to norm of f tilde, that is equal to 1. Consequently, x belongs to y closure if and only if x belongs to x and f of x, that is equal to distance between a and y closure, that is equal to distance between x and y closure, distance between x and y closure. This is equal to 0 since x belongs to y closure whenever f belongs to x12 and f restricted to y equal to 0. Now we prove part C. So let a1, a2, etc. am be linearly independent set in X. Let yj equal to span of AI such that 1 less than or equal to I less than or equal to M, I not equal to J. This Yj is span of A1, A2, etc. Aj minus 1, Aj plus 1, etc. Am. Then Yj is finite dimensional. Therefore, Yj is closed in X by 5.4b. We have Aj does not belongs to Yj and Yj equal to Yj closure since Yj is closed. Therefore, by part B of this theorem, there is some Gj in X12 such that Gj equal to 0 on Yj and Gj of Aj equal to distance between Aj and Yj. This is not equal to 0 since Aj does not belong to Yj. Now let Fj is equal to Gj divided by distance between Aj and Yj. Then Fj belongs to X12 and Fj of Ai equal to delta Ij for 1 less than or equal to I comma j less than or equal to m. Since this is because since Fj of Aj is Gj of Aj divided by distance between Aj and Yj, and you know this is distance between Aj and Yj divided by distance between Aj and Yj, so that is equal to 1. And for I not equal to j, Fj of Ai, that is equal to Gj of Ai divided by distance between Aj and Yj. We have Ai belongs to Yj, therefore Gj of Ai is 0. Therefore, this is equal to 0. So that's all for the day. Have a nice day.